Last time we looked at permutations and some of their properties under composition. Those properties, taken abstractly, give the axioms for a group. So, a group consists of two pieces of data. The first is a set G, and the second is, I'll denote it by dot, it's a binary operation. Okay, a binary operation is just an operation which takes two inputs and gives out one output. So you can think of it as a function from G cross G to G. It takes x comma y as inputs, two elements of G, and spits out x dot y. Okay, this set and this binary operation need to satisfy the following axioms, which we saw last time. So the first axiom is associativity, which says that if you have three elements x, y, z in G, then you can apply this operation dot to them to get a single element in two different ways. One is, okay, first you take x dot y and then you dot that with z. The other is you take y dot z and then you take x dot whatever you get when you do y dot z. And associativity says that these are the same. The second axiom is the axiom of the identity. So this axiom says that there exists element of G, which I will denote here by ID, such that x dot identity is equal to x, and that's also identity dot x for all x in G. So what we're saying is that this element is such that you take any element in G and you multiply it either on the left or on the right by identity, then you will get back that element. And the third axiom is the axiom of the inverse. So this axiom says that for every element x of G, there exists another element x inverse of G, such that x dot x inverse is identity, and that's the same as x inverse dot x. So these are the axioms for a group. Let's look at some examples. So we've already seen one example last time, namely Sn, the set of permutations of on n letters, which is nothing but the set of bijections from the set 1 dot 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 n to 1 dot to itself, and this is a group under the operation of composition. Another example, a really simple example which you would have encountered in primary school, is the group of integers under addition. So this is the set of all integers, positive, negative and 0, and this is the operation of addition. So you know that integer addition has the associativity property. In addition, the inverse is really the number minus x plus minus x. Firstly, we need to talk about the identity axiom. So what's the identity in the integers? So in the integers, the identity is the element 0. X plus 0 is equal to x, which is 0 plus x. Right, so the group theoretic identity in the integers is 0, and the inverse is actually the negative. X plus minus x is equal to 0, which is minus x plus x. Okay, so the integers under addition form a group. Let me give you a slightly more interesting example, and this is you fix an integer capital N and you look at the group of residue classes mod n under addition. So this is the group of what is sometimes called clock arithmetic. So every day in our clocks we use clock arithmetic, that is, if it's 9 o'clock right now, then 4 hours later it's going to be 1 o'clock, right? Because 9 plus 4 is 13, and when you divide 13 by 12, the remainder that you get is 1. So this is the arithmetic of remainders modulo n. So so in this as a set, this z mod nz is the set 0, 1 up to n minus 1, is the set of all possible remainders that you can get upon division by n. And given two elements x and y in this set, x plus y is the remainder when x plus y as an integer is divided by n. Okay, we do this all the time with clocks, as I said. So in the 12-hour clock arithmetic, when n is equal to 12, 9 plus 9 is 18, and when you divide 18 by 12, the remainder is 6. So 9 plus 9 is 6 in z mod 12z. And it's easy to see that 0 is the identity here. Well, associativity is also very easy, because ordinary addition has associativity, and then you're taking remainders. So clock this addition modulo n will also satisfy associativity. The identity element is 0, and what is the inverse? So in this 0 is its own inverse. I'll write it as minus somehow because we're using plus sign. So the inverse of 0 is 0. The inverse of 1 is n minus 1, because n minus 1 plus 1 is n, and when you divide n by n, the remainder is 0. And the inverse of minus 2 is n minus 2, and so on. Okay, and let me give you a non-example of group. Take the integers, but instead of taking addition, take multiplication. This is not a group. Why? Well, does it have an identity? So 0 is not an identity for multiplication, because 0 into x is 0, but the identity axiom for the group says that 0 into x should be x. Okay, so maybe 1 into x is x. That works, except when x is equal to 0. In that case, so when x is not 0, 1 into x is x. When x is 0, also this is 0. Okay, so it also has an identity. So the identity is one. Okay, but inverse. So let's look at inverse. So what is the inverse of 2, for example? So 2 into what is equal to 1? Well, there is no integer which if you multiply by 2 you will get 1. There is a rational number, but there is no integer which if you multiply by 2 you will get 1. So it does not satisfy the identity, the inverse axiom. So this is not a group. Okay, and similarly you can see that, for example, z mod 4z under multiplication is not a group. Here I am doing multiplication mod 4, which means I take two elements and I multiply them, and then I divide by 4 and look at the remainder. So in this, for example, 3 into 3 is 9 divided by 4 leaves the remainder of 1. So 3 into 3 is 1 in Z mod 4. But here again, there is no inverse. For example, 0 itself doesn't have an inverse. Okay, so think about this. The identity here is going to be 1 because we're talking about multiplication. But no matter what you multiply 0 by, you're not going to get 1. So this is also not a group. So now let's look at some simple properties of groups that we can derive just from the axiom. So the first property is cancellation. What it says is that suppose you have x, y, z, 3 elements of the group G, and suppose x dot z is equal to y dot z. So then x is equal to y. So let's prove this just using the group axioms. So what we know is x dot z is equal to y dot z. Now by the identity axiom we know that there is an element which when multiplied by z gives the identity. So this is z inverse. So let's write that down. X dot z inverse is y dot z inverse. And now we'll use associativity. So this z inverse we have because of the inverse axiom, and now let's use associativity. So we get x dot z inverse is equal to y dot z inverse. So this uses associativity. And now what is z dot z inverse? Well, that's just identity. And well, x dot identity is x and y dot identity is y. So what we've shown is, so this uses the identity property. What we've shown is that if x dot z is y dot z, then x is equal to y. You can think of this as a cancellation rule. You have x, an equation which says x dot z is y dot z, then so that you can cancel z on both sides and get that x is equal to y. Okay. Another simple property of groups is the uniqueness of the identity. In the axioms, we just said that there exists an element identity of G which has the property that x times identity is equal to identity times x is equal to x for all x in G. But what I want to say is that there is exactly one such element. So suppose we had two elements. Suppose identity and identity prime are both such that x dot identity is x for all x in G, and x dot identity prime is x for all x in G. Actually, you don't even need this for all x in G. Even if there's one such x, then what you get is x dot identity is equal to x dot identity prime. And then you use cancellation. Oops, not that way. I want to cancel the x. And you get identity is equal to identity prime using cancellation. So there's only one identity in any group G. And here's a little exercise for you. Prove the uniqueness of inverse. Okay, now let me tell you how we can store a group in a computer, or sort of more abstractly store a group. So the examples we looked at came from some other branch of mathematics, such as the theory of permutations, or in the case of integers, from number theory, addition of numbers, addition of integers, mod n. But more generally, a group is just a set, and we need to keep track of this function g cross g to g. So once we specify the elements of G and this function G cross G to G, we have specified the group. And so this can be stored in the form of a table. Let me do this with an example. Let's look at the group Z mod 3Z. So this has elements 0, 1, 2, and we know how to add these things. So I'll write down this G cross G to G in the form of a table. So we have going to have rows and columns, both indexed by the elements of the group. So this, I'll call these maybe X, and I'll call this Y, and in this table I'll store here X dot Y. So in this case it's going to be X plus Y mod 3. So 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2 is 2, 1 plus 0 is 1, 1 plus 1 is 2, 1 plus 2 is 3, which is the same as 0 mod 3, 2 plus 0 is 0, 2 plus 1 is 0, and 2 plus 2 is 4, which is 1 mod 3. This is called the multiplication table of the group Z mod 3. And once you write down the multiplication table, you've completely specified the group, because you've told us what dot does to any two elements. The multiplications table has rows and columns indexed by the elements of the group, and the entries are the products of the elements X dot Y. Okay, so let's now try to see, suppose we have a group G with two elements. So suppose G has two elements. So here's the question: what groups have two elements? So one example you can think of readily is Z mod 2Z, right? So what is its multiplication table? 1 plus 1 is 0. Okay, but suppose I have some other group with two elements. So now suppose G is some other group with two elements. Then one of those elements is going to be the identity, and the other element is going to be something, we'll call it A. Okay, so this group is going to have two elements, identity and A. And let's write down the multiplication table. So I have to write down X dot Y. What can it be in this group? Now we already know that identity into identity, well, is the identity A into identity by the identity axiom is A. Identity into A is also A by the identity axiom. What we don't know is what is A dot A. Okay, now A dot A, there are two possibilities. Either it could be A or it could be identity. So let me just put down A here and see if this gives rise to a group. So what I have is this binary operation which says that identity into identity is identity, identity into A is A into identity is A, and A into A is A. Now question is, does this operation satisfy the group axioms? So it satisfies the identity axiom, because anything into identity either on the left or the right is that thing itself. But what is the inverse of A in this group? So is there an element which if I multiply by A, I get the identity? Well, A into identity is A, and A into A is also A. So there is no inverse of the element A. So we cannot have A over here. Okay, so instead let's put identity. So I'm changing this, A into A is identity. And now you can check in fact that this gives rise to a group. Okay, so here I have two groups of with two elements. They look rather similar, right? If instead of identity I put 0 and instead of A I put 1, then this table here just becomes exactly this table just by substitution of symbols. So this is an example of group isomorphism. So I have this function, let's call this, let's not call this one G now, let's call it Z mod 2. So take this function f, where f of 0 is identity and f of 1 is A. Then what we have is f of x dot y is f of x dot f of y. So this first x dot y is in the group Z mod 2, and then this dot here f of x dot f of y is in the group G here, and this function is a bijection, right? So what we are saying is that these two groups are isomorphic. So suppose I have two groups G dot and H, just to distinguish it I'll say star, are isomorphic if there exists a bijection f from G to H such that f of x dot y is f of x star f of y. So what we had is that in the example on the previous page we have that G is isomorphic to Z mod 2Z, and we denote this situation by writing G is isomorphic to S. And what we've shown here in this example is that if you have any group with two elements, then it has to be isomorphic to Z mod 2Z. Okay, let's try this with three elements. So suppose you have a group with three elements. So we have a group, it's going to have three elements. So we have identity, A and B. Identity, A and B. And now I already know that this row is going to be the same and here it's going to be the same because of the identity property. Now let me ask you, can A dot A be equal to A? Now the objection that we had earlier that A must have an inverse is no longer valid, because maybe you could have A dot B is equal to identity. So question is, can A dot A be equal to A? But by the cancellation, so I can write this as A dot A is identity dot A, and then if I use cancellation I get A is equal to identity. So A dot A is equal to A implies that A is the identity. So I cannot have A dot A is equal to A. I have to have A dot A is equal to B. And similarly B dot B has to be A, it cannot be B. And now I have the identity axiom which says that A dot something has to be identity. So I better have identity here, and identity dot A is equal to something dot A is equal to identity. So have identity here. So if a group has 3 elements, then its multiplication table has to have this form, and this is exactly the same as the multiplication table of Z mod 3Z as you calculated earlier. So if you take f of 0 to be identity, f of 1 to be A, f of 2 to be B, then you'll get an isomorphism from Z mod 3Z. So in this lecture, we've seen what is the abstract definition of a group. It's given, it's as a set with a binary operation, and this binary operation must satisfy the axioms of associativity, identity, and inverse. Then we looked at some examples of groups, some non-examples, and we talked about when two groups are isomorphic.